All right, so this is our initial trigonometric ratios lesson, kind of a sneak preview of trigonometry as a branch of mathematics that you'll study a little bit more extensively during pre-cal and extended into calculus and stuff. All right, so what our goal here is to discover and use the three main trig ratios. And those trig, when I say trig, of course, I'm usually shortening that word trigonometric. Those trig ratios are on your calculator as a sine, a cosine, and a tangent. Here they are, sin, cos, and tangent. Those are the three main ones, and there's actually three other ones, which are the reciprocals of those, that you won't have to talk about, really, until you get into pre-cal. All right, now, there aren't actual challenge problems attached to this one. It is one of those worksheets which extends out the lesson just a little bit of reading that's going to go along with that on the more tangent ratios worksheet. All right, so if you take a look at the image here about discovering the three main trigonometric ratios, got something that looks like a totem pole, might call to mind a summer camp, and you know those summer camps often have some sort of Native American bent to them, maybe a name of it, Sohcahtoa, something like that. It has something to do with the trig ratios, as we'll see. Okay, so in this warm-up exercise, we want to find the value of x, and we got ourselves a right triangle. This should be a piece of cake. I love right triangles. Solving right triangles is easy. Pythagorean theorem, special right triangles and stuff like that. I should be able to do it pretty easily, right? All right, let's see. I've got x down here for one of the legs, 5 over here for the other leg, and 20 degrees. It's definitely not special. It would need to be either a 45 or a 30 or a 60. It's not special, so that doesn't help. And I can't use the Pythagorean theorem because I don't have the hypotenuse. So as it sets, it looks like we don't have enough information. Information? That's not how you spell that word. Question mark? Or do we? All right, well, as it sets, we don't know enough in order to actually figure the thing out. But what if I did this? What if I gave you another triangle to compare that to? What's the relationship between these two triangles? Well, notice that they both are right angles, of course, right triangles. This one's 20, that one's 20. Those two acute angles are congruent to each other, which means that these two right triangles are similar to each other. And if we have similar triangles, then that means that their sides are proportional. So now I should be able to actually solve this problem by just setting up a proportion. Now, I can set up this proportion a number of different ways. The way that I'm going to choose to set it up is x, the side that I'm looking for, over the 5 that's right here, is equal to, and then I keep it in the same order, which is, let's see, 8.25 centimeters over 3, right? And I could just cross multiply. I don't even have to cross multiply. I would just multiply this 5 up to the top here and get x is equal to 5 times 8.25 over 3. Right? I can just throw that right into the calculator. 5 times 8.25, all of that divided by 3, and we get 13.75. Let's see, does that make sense that this piece down here is 13.75? What the heck is that? Try that again. 75. All right. Yeah, but here's the thing, though. Like, what are the chances that you're going to have, like, another right triangle that's similar to the one that you have with all the pieces already measured for you? It seems kind of unlikely. Except for, what if I told you that this ratio right here, this 8.25 over 3, is stored in the calculator? We're just going to learn how to access that particular ratio. That's basically what this whole lesson's about, is that these trigonometric ratios, these trig ratios, sine, cosine, or tangent, they have to do with right triangles and its ratios of sides like this one. This 8.25 over 3, and I want to just know in the calculator how to access them. And like I said, has to do with something like this, these things. Whoa, what the heck's going on there? We usually don't do that though. Yeah, that's crazy. Here, let me get rid of that. That's confusing. Tippity tappity tap. All right, anyway. So let's go back to the slideshow here and get a little bit of a history lesson. Like, where's all this stuff coming from? So right triangle trigonometry, first of all, understand that right triangle trigonometry came after trigonometry. The sine, the cosine, and tangent weren't originally attached to right triangles, but eventually they got attached to right triangles for a very specific reason, very useful reason, and it definitely gives us an opportunity to understand trigonometry in a high school geometry class. Anyway, so right triangle trigonometry is the study of relationships between the sides and angles of right triangles. And these relationships can be used to make indirect measurements like those using similar triangles. And that's what we did in that warm-up exercise. The dude over here that's pointing out those stars, that's Ptolemy, whose name you might remember from something like the Ptolemaic system or explanation of the solar system that was eventually replaced by the Copernican system. So this guy is the one that's responsible for putting Earth in the center of our solar system. And then Copernicus turned around and said, you know what? I don't think that's very accurate. I'm pretty sure it's the sun. So early mathematicians discovered trig by measuring the ratios of the sides of different triangles. They noticed that when the ratio of the short leg to the long leg was close to a specific number, then the angle that's opposite that shorter leg was also close to a specific number. So here's again a picture of Ptolemy, and he's looks like he's looking through a device to measure maybe the positions of stars and stuff. You know, astronomy, or maybe it's astrology. It's one of those. So in this example, in every right triangle in which the ratio of the short leg to the long leg is 3 over 5, then the opposite side to the let me read that again. The angle opposite the shorter leg measures close to 31 degrees. Look at the pictures right down here. So from this, what is a good approximation for x? I'll come over here so I can actually write on the screen a little bit. Okay, so notice that, of course, they're all right triangles, and each one of them have a 31 degree angle, which means that these triangles are similar by angle, which means that the ratios of their sides should always be the same. And according to this, the ratio of the sides is about 3/5. So look at the next one. We have 9 over 15. If I divide the top and bottom by 3, we get 3/5. If we look at the next one, 6 over 10, divide that one by 2, you get 3/5 also. So the same thing should be happening over here. I have got something over 55 that's supposed to be equal to 3/5. Well, it looks like all I got to do is multiply that by, what, 11? So x has got to be 33. So this is basically how trig is going to work. It's just that I'm going to know this because it's put into the calculator for me. Right? Let's look at another one of these examples. In every right triangle in which the ratio of the shorter leg to the longer leg is 9 over 10, the angle that's opposite the shorter leg measures pretty close to 42 degrees. So what's a good approximation for y? I'm going to do the same kind of thing over here. So again, these triangles are all similar right triangles because their angles are the same. And the ratio for this first one, for this short side to the somewhat longer leg, is 9 over 10. And for the second one, we have 27 over 30. If you divide that by 3, you definitely get 9 over 10. All right, so far so good. What about this 4.5 over 5? This one, instead of dividing, if we multiply by 2, we'd get 9 over 10. So again, a 42 degree angle opposite that. And let's see, if I use that same exact principle here, that some number over 90 is supposed to be equal to 9 over 10. So it looks like in this case we're multiplying by 9, which makes 9 times 9 and 81 for this missing side. Okay, so again, that's basically a sneak preview of the kind of things that we're going to be doing for trigonometry. And this one in particular, both of these examples that we just looked at, is one of those specific trig ratios. And what are those trig ratios? Sine, cosine, and tangent. Commonly abbreviated as sin, cos, cos, and tan, tan. Right? And that's how you usually see them on a calculator. In the next video, we'll do a little GeoGebra investigation to try to figure out what exactly does the sine, the cosine, and the tangent ratios measure.